Today we have Daniel J. Bernstein, Nadia Henninger, and Tanya Lange. And they will talk about RSA factorization in the real world. The talk is called Facthacks.
Thank you. So we're going to start with a crypto lecture in 5 minutes. So just to begin, since we're talking about RSA, here is a picture of RSA for you. RSA is the first published public key crypto system. So by a public key crypto system, what I mean is a crypto system that has 2 keys. Instead of just having, one key, you might think, okay, you encrypt a message to that key and you decrypt a message to that key. That is a symmetric crypto system. A public key crypto system has 2 keys. One is the public key and one is the private key. And the public key you publish to the world, and anyone can use that key to encrypt a message, especially to you. And only you who have the private key can decrypt that. So the RSA paper was the first published public key crypto system. That was in 1977. This revolutionized cryptography and enabled the development of the internet. So 35 years later, RSA is still the most commonly used public key crypto system. If you ever use the internet, you probably use it every day. So here is a sample SSL certificate, which uses RSA. If you use SSH, you probably have an SSH key, which probably is RSA. Before I launch into the math, I want to explain what we're doing here. We wanted to, since you guys are hackers, you like code, and instead of formulas, so we wanted to give you formulas in code. And so what we are giving you is working Python code for all of the math that we're going to do. And in order to do that, we're going to use some software called Sage. Sage is free open source mathematics software, and it is available at this URL, sagemath.org. It's based off of Python, so it's very simple if you know Python. And it has a nice sort of interpreter that you can use just like Python. Here, and here's an example, 2 times 3 equals 6. But there are some differences. For example, the caret, instead of in Python it's XOR, in Sage it's exponentiation. So 2 to the 3 is 8 in Sage. And the other nice thing about Sage is that it has lots of useful mathematical libraries. For example, if I, in the Sage interpreter, say factor 15, it helpfully tells me 3 times 5. That's pretty great. It also does a lot more advanced things. For example, it can represent polynomials. I can say factor the polynomial x squared minus 1, and it helpfully tells me the answer to that. So now that we've gone through what is Sage, I want to explain how to do RSA. So perhaps some of you have seen this before. In order to generate an RSA key, the first thing that you do is you generate 2 large random primes. So if we want a 1024-bit RSA key, we generate 2 primes of size 2 to the 512. So 5 12-bit primes, P and Q. In order to generate the public key, you multiply together P and Q and you get some N. N has 1024 bits. And then you have what's known as the public exponent, which you can choose 3 or 65537 or 35, or it really doesn't matter what you choose. These are some of the most commonly used values. Now, in order to generate a private key, you choose D, the decryption exponent, to be the modular inverse of E mod P minus 1 times Q minus 1. It doesn't matter why so much for this talk, but here is the formula, or here's the command to do this in Sage. So now we have a public key and a private key that are pairs. And in RSA, if you want to encrypt a message, you raise your message to the eth power mod n. So you can do that with your public key here. And similarly, decryption, you raise the ciphertext to the deth power mod n, and that will give you the message back out again. Fairly simple. Now, I'm lying to you slightly if you read this talk. Absolutely do not implement RSA this way. You must pad your message. This is public service warning. So we offered to tell you about factoring. What is the relationship between RSA and factoring? So Now you can see easily from the formula from the private key here that if you know how to factor n into its prime factors p and q, then you can just compute d, the decryption exponent, your private key. So clearly, if you can factor n, you can compute the private key. But we don't actually know that factoring is the only way to break RSA. So there might be some way that you can compute messages from ciphertext that doesn't actually reveal the private key. And there's no proof either way that this is or is not possible. The last thing that I want to mention here, just to clarify things, some of you who might have taken complexity or algorithms courses or a beginning CS course, you might have heard of NP hardness, the P versus NP problem. And I just want to clarify that factoring is not known to be NP hard. Every computer scientist would love it if we could actually generate a crypto system which is known to be based off of average case NP hardness, and we don't know how to do that, and RSA is not doing that. In addition, the factoring problem is probably not NP hard. So the question is, how hard is factoring, since factoring is the best way that we know to break the most commonly used public key crypto system on the internet? Well, I showed you some examples before where Sage had this helpful little factor function. So how well does it work? How long do people think this takes? Two 32-bit integers multiplied together. I heard a couple seconds. 0.01 seconds. This is on this computer. How about 64-bit integers, two of them multiplied together? So this is 128-bit RSA modulus. Any guesses? 1 minute. Nope. 0.1 seconds. How about two 96-bit integers multiplied together? A couple minutes? 4 seconds. How about two 128-bit integers multiplied together? This is a 256-bit RSA modulus. No guesses? All right, 500 seconds. So at this point, it's starting to get a little bit iffy if I'm, sitting on the plane trying to do this on battery power. But clearly, this is growing faster than linear in the size of the key. So what is actually going on? Well,
okay. Turns out these factoring functions, they do look like they're getting pretty slow, but wait a minute. Do we actually have to use this factor function if it's getting really slow? Maybe instead of trying to use Sage's factor function, maybe we could just guess what the prime was. Now, as an RSA user, you might not think that this is a threat, having somebody guess your prime, because there's some way to count the number of primes, number of 512-bit primes, and there's more than 2 to the 500 512-bit primes. And if your random number generator is giving you any of those 512-bit primes with the same chance, then any particular prime that the attacker guesses and just tries dividing n by that, sees if it's evenly divisible, well, any particular prime has only a 2 to the minus 500 chance of being guessed by the attacker. And even if the attacker tries a huge number of times, they'll never guess your prime. Except, what if your random number generator is working really, really badly and doesn't give you 2 to the 500 different primes? What if it only gives you, say, 2 to the 40 different primes? And then suddenly the attacker could, well, try figuring out what those primes are. So here's how the attacker looks at this. The attacker says, okay, I'm going to target your public key. I'm going to take your big N, which is your secret key, your public key is big N. It's your secret key P times your secret key Q, your private P and Q. And he's trying to figure out the P and Q given N. So what he does is he takes a bunch of devices that are out there, and he looks at how they work, or downloads a bunch of software which generates keys, and then using that software or using those devices, he tries generating a bunch of P's and Q's for himself, using whatever the random number generator is in that device or in that software. And then that's something which maybe the random number generator works really badly, and maybe you're using that device too. So the attacker tries each of the primes that he sees from this device and tries seeing, does that prime divide your N? And if you were using that device and it doesn't generate very many primes, then maybe he gets lucky and finds your prime, because the device has generated the same prime for him that it generated for you. Now, does anybody actually build devices which screw up random numbers this badly? As a matter of fact, yes, bears do shit in the woods. So there are some famous examples. We don't have a huge number of historical discussions in this talk, but just a few examples here. Goldberg and Wagner totally broke the original Netscape generation of public keys. There are only something like 2 to the 47 possible keys, which was a countable number. So they could figure out all the possible keys that Netscape could generate if they knew when you generated a key, which was often very predictable. Another example, the Debian bug, the horrendous failure for SSH and lots of other applications from a few years ago. Debian and Ubuntu for a year and a half were generating only, well, fewer than 1 million possible public keys. So complete disasters of random number generation. But if you want to add to this list, if you want to do more and more of these find bad random number generators, you have to say, okay, what's the next device out there that might have been screwed up? Let's look at it, look at the code, see what kind of primes it generates, and does it do badly? It takes some real work to figure this out. Wouldn't it be nice if there was a systematic way to just, without having to do a lot of work to look at each device, each piece of software, wouldn't it be nice to just figure out, oh yeah, let's just magically figure out if there's any primes out there generated from bad random number generators. And you can imagine, here's the easy attack. Here's the systematic way to do this. You take 2 users, so you and you each have a public key, and we're going to grab those public keys, N1, oops, well, I'll leave this up here, N1 and N2, and then hope that these N1 and N2 share a prime. So N1 is some prime p times some q1, and N2 is some same prime p times some different q2. Now, this could happen. You could have N1 and N2 sharing both primes. That would be legitimate, that 2 people who are actually the same web server sharing their keys, sharing their certificates, they know they're doing this. You can get the same public key from 2 places. Google has their keys copied to tens of thousands of servers. That's not a surprise. But if you have 2 different public keys, they shouldn't be sharing primes. But what if they do? Well, here's this magic Euclid's algorithm, which will just print out the shared prime p. So it's a very simple algorithm. It just takes one of the numbers, say N1, and let's say N1's a smaller one and N2 is the bigger one. It divides N2 by N1 and replaces N2 by the remainder and then switches the numbers, and that's exactly what this code does. The N2% N1, that's again the N2 mod N1, the least remainder when you divide N2 by N1. And then the result, once you get down, one of the numbers gets down to 0, the other number is exactly the shared prime. So this is an amazing algorithm. Here's just a little manual example, not with big 512, 1024-bit keys. This is with just tiny little, I guess, 8-bit primes. 16-bit, well, it looks more like 13-bit keys. So 2 numbers coming in. N1 is 4187, N2 is 5989. And you can see if you keep dividing one number by the other, replacing it by the remainder, do that a few times, you quickly get down to 0. And the number right before the 0 in the middle of the slide is 53. And that 53 is a shared prime between these 2 small keys. If you scale this up, if you do this computation for bigger numbers, then here's another timing example. It's still really, really fast. In the middle of this slide, this is doing 10 24-bit keys that share a 512-bit prime. You can figure out this 512-bit prime so quickly that the timing there, 0.00 seconds, can't even see how fast it is. Okay, so that's Euclid's algorithm. Now you can actually do this for tons and tons of keys. You download, say, millions, tens of millions of keys from the internet, all the different SSL servers, maybe go for some SSH keys. You download tons and tons of public keys, and then you try all the pairs with Euclid's algorithm. And it's so fast that you can do this, but actually you can do better. So there's an algorithm, batch GCD algorithm, which takes a whole bunch of keys and figures out which of those keys share primes with the others. Much, much faster than trying every pair. So you don't have to try every pair. It's kind of like sorting, that it's about that kind of speed instead of having to try every pair. If you have tens of millions, you don't have to do tens of millions times tens of millions of pairs. You just have to pretty much read through the whole list once. So what does this batch GCD algorithm do? Well, it's figuring out for the first N1, instead of computing the greatest common divisor, the Euclid result for N1 and N2, and for N1 and N3 and so on, it figures out the product of N2, N3, N4, and so on, takes the greatest common divisor of that with N1. Applies Euclid's algorithm to that, and then does a similar thing for N2 and for N3 and so on. And each of those is going to show you whether n1 or n2 or n3, it's going to show you whether they share some prime with any of the other n sub i's. Now this, if you did exactly the computation shown on this slide in the math formulas, it would still be too slow. But the batch GCD algorithm finds redundancies in these GCDs. And here's exactly what it does. It figures out the product of all of the keys. So you take, say, 1 million keys and you multiply them all together. And that's done with the code here. What you do, maybe I'll just skip to the bottom. You see numbers 10, 20, 30, 40. You build a product tree. So you take 10 times 20, compute 200. Take the next pair, 30 times 40, compute 1,200. Then take the pair of products, 200 times 1,200. And if you add more numbers, you have more levels in the tree. And that's exactly what the Python, well, the Sage code does here. And then the last step of the algorithm is kind of going down the tree, building a remainder tree. So what's happening here, to figure out the greatest common divisor of n1 with the product of all the other keys, the idea is to take this product, which is called big R on this slide, take the product of all the keys and then divide that by n1 squared, and then take the remainder, so R mod n1 squared, divide by n1. And then compute the greatest common divisor of n1 with that. And the amazing fact is that's exactly the greatest common divisor we're looking for. And then what this little Sage script does is it takes R and divides R by, well, a bunch of n's in a really fast way. And then at the bottom, once it's figured out R mod n1 squared, R mod n2 squared, and so on, divides those by n1 and n2, takes the greatest common divisor with n1 and n2. And that's exactly telling you, the outputs here that are different from 1 are exactly telling you which n sub i's share a prime with some others. It's very remarkably short little scripts and work quite well. Here's how fast these are. So on some 800 megahertz core, if you try this for, say, 100 numbers, then just 100 random 1024-bit numbers, which it doesn't matter what the numbers are, it'll always run at the same speed. Then that takes 0.05 seconds. If you have 10 times as many numbers, it takes about 20 times as long. And if you have another 10 times as many numbers, it takes about 20 times as long. And it keeps scaling up like that. So you can get to millions or tens of millions of numbers, and it still finishes in a reasonable amount of time. So amazingly fast algorithm. You don't have to scale this up to like 2 to the 50 or 2 to the 100 keys. There's only, say, tens of millions of keys out there. And this runs reasonably fast. OK. Can you actually hope for this to work? Are random number generators really this bad? Well, there's a 2012 paper from Henninger. That's the same Henninger we have sitting here, and Durmerk, Wistrow, and Halderman. This got the Best Paper Award at Usenix Security 2012. And what they did was they tried exactly this on tens of millions of keys out there and factored tens of thousands of keys. Admittedly, they used a C version of this instead of these Sage scripts, but the Sage script will go up to millions. It's just when you get beyond that, you want to write it in C to deal with using a lot of memory. But you can use exactly these scripts for pretty large chunks of keys. And so they factored tens of thousands of keys and said that these keys are, well, typically not your bank keys. They're going to be, say, keys for your home router. So the vulnerable devices are not going to be, say, a big server out there. The vulnerable devices will be your Fritz box. Thank you, Nadia. So, okay, so what's going on? Well, it's good to read the paper. Go to factorable.net, and you get tons of analysis of why this happened and why these devices are generating guessable numbers. I mean, numbers that are so non-random that they get repeated between a lot of keys out there. There was at the same time another team that, like within days, they announced the same result. They independently did the same computation. They said, yeah, we've also downloaded a bunch of keys and factored as many as we could with basically the same algorithm. And then, so at the end of it, yeah, we factored tens of thousands of keys. That paper has no analysis. So they're like, yeah, there's keys. They share primes for some reason. I guess e-commerce is dead. Got to change your bank keys. Call the New York Times. So there's the New York Times article. Flaw found in an online encryption method. I also like the advertising on the side here, like iron key on the top and then encrypt, decrypt, and access MySQL data in real time. Try it free for 30 days. I secured my cloud data. Have you? Awesome advertising there. Yeah, once you've found that there's a problem like this, then of course you start looking around for more and more places where you might have some bad randomness. For example, there's a paper, or at least slides, by Chow in Taiwan saying, okay, they took 2 million Taiwan citizen digital certificates and did some GCDs and found that 103 of those were factorable. So anybody who downloaded these certificates, which apparently are used in Taiwan for like paying your taxes, talking to banks, I don't know, but paying taxes is one that I've checked. So 103 people out there have these Taiwan citizen digital certificates where you're supposed to have in this database things like the names of the people and their ID numbers, but you aren't supposed to have their secret keys. The whole point is those are supposed to be private, kept on some smart cards that are issued to the citizens in Taiwan. And the randomness generation is so bad that 103 of those keys have now been factored. Okay, the smart card manufacturer, I also like this quote. It's a company based in Munich called Giesecke and Devrient, and their motto is creating confidence.
So there's going to be more of that, don't worry. But we promised a bit more than just factoring bad keys or the keys with the primes. Now, if you find another number like this one, so here's coming some more of math stuff. So if you see a number like this and you observe this last digit, then yes, it's very easy for you to see it's divisible by 5. So if you find such a key that it's easy to break, and if you're a computer rather than a human being, you look at lots and lots of those numbers, you have a list of small primes stored, and what you're going to do is just trial division. So if there's any small factor, it's very easy to find with trial division, or what Dan showed with all the remainder trees, you can also do this for batch trial division. So assuming that you're looking for a prime p somewhere, then you go linearly all the way up to the p, and there are about p over log p many primes before you find this p. For each of them, you just do an exact division. If it works, fine, you found a factor, otherwise not. Now, this is not going to work against your normal keys. I know that in the example that Dan mentioned by Wagner and Goldberg, that they found one factor which had a 9 in there, but usually your keys don't have a 9. Now, for slightly larger numbers, there is a method due to polish. So if you see respectable number here, there is no obvious divisibility of this one. One thing you can try is a walk. Well, we call this a walk. You start with some random number smaller than n and some offset here. Oh yeah, I should also say all those scripts are available at this URL. So if you go to facthacks.crypto, then you find all the scripts if you want to play with it at the same time, including this one and some explanations and such. So what you do is you start off 2 different numbers. One at each step squares it and adds c, and the other one squares it, adds c, and squares it again and adds a c. Each time computing mod n. So you have 2 sequences running around. One is at twice the speed as the other one. And at every step, you check whether the GCD of this number n and the difference between the 2 walks has anything interesting. Now, if your n is an RSA modulus, the only thing interesting could either be p or q. So for this particular number, when I run this, I find 2053 after a few milliseconds. So this is, again, a cooked-up example. You won't find such a small factor if you're trying a general RSA factor. Otherwise, your numbers would be totally busted. But this shows if you have a small number in there, it's very easy to find. Or later on, when Dan is talking about the number-filled sieve, this is an interesting subroutine. So if you ever need to find small numbers, then sure, trial division is very easy for really small numbers. Taking this long, this one, square root of p, is much faster already. Now, even faster than that is a method also due to Pollard called Pollard's p-1 method. Here's again an innocent-looking number n. You see the numbers get larger, so this is a 256-bit number. in order to deal with such a number, there is one step which is expensive, but this you would do only once for all different numbers you want to try, namely compute a big integer which has lots of little factors. So you take the least common multiples from 1, 2, 3, 4, 5. Okay, once you hit the 4, you have another 2 in there. So there's lots and lots of powers of 2, lots and lots of powers of 3. And then the larger primes only appear like once. But you're not going up to 256 or 128 anywhere. You're sticking here at 22 bits. And then you use the same function that Nadia explained in the RSA computation, namely the modular exponentiation. So you take the power of 2 to the y, this huge number, but the whole computation mod n. So this whole thing never grows beyond this 256-bit number, or for a real-world example would be a 1,000-bit number. And then you compute the GCD of this number and n. And for this particular one, again, it's a cooked-up example, you get a factor. Now this factor is actually 120 bits. This is not a small factor. So if you were using 256-bit numbers, this is something that could happen to you. And nevertheless, this method would find it. So this finds much larger factors than trial division or the row method in the same amount of time. But it doesn't work for all primes. It works for primes which are kind of special. Now, what's special about this prime or the other factor? If you take p and subtract -1, hence the name p-1 method, and factor that thing, that has lots and lots of small numbers. So that's something we call smooth. So a smooth number doesn't have big factors. So a prime is like the least smooth number you can imagine. And 2 to the power large is the most smooth number. So lots of little factors means smooth. And this largest factor happens to be 21.7 bits, which is why I chose the 22 bits here. So as soon as I run over the largest prime in p-1 with this exponent y here, then I do find this factor. Now, if you thought this was math, there is even more scary math, namely, there is methods which are generalizing this p-1 method using elliptic curves. So if you listen to the crypto advertisement, elliptic curves are usually something very good, something you should have on your smart card, it's faster than RSA and so on. That's the same type of elliptic curve, but here elliptic curves come in as an attack tool. There's a method called the elliptic curve method, ECM, which is a generalization of this p-1 method and does not need anything special. I mean, avoiding such primes is easy. If you look into older standards, they all warn about make sure to use strong primes, make sure to check that your p-1 is not smooth. And of course, you don't want your p-1 to be smooth because otherwise this attack works. But if I have some elliptic curve, a different type of prime is weak for that curve. And I have many elliptic curves. For each of the curves, some primes are weak. You can't exclude this method. So the only thing you can do is just, well, choose your prime large enough and hope that make sure p-1 doesn't get it and hope that the next 3 elliptic curves won't get it. So elliptic curves are good for attacking. It's still not the fastest method out there, but it's a good method against random factoring, random factoring. It's not the best method for finding RSA factors, but if you have a number which is most likely not too non-smooth, then it's a good method. Now this is what you do for finding small factors. To show some method for big factors, now here that is a big number. But this is what I would call factorization by inspection. What's wrong with this number? I mean, this number is not small, and it won't have small factors, I promise you this. But it says, so it's a decimal representation, so 9 is the digit before 0. So this looks very close to a power of 10. Actually, this is very close to a power, 10 to the 340. And if you take the square root of it, then you almost exactly hit 10 to the 170. So this example was cooked up as taking 2 primes, namely 10 to the 170 minus 33 and 10 to the 170 plus 63, and multiplying them. So if you see lots of zeros and lots of nines, then you know that you're very close to a certain power. Now, in real life, this wouldn't be a power of 10, it would be a power of 2. And there actually are some examples. There's a famous story of a letter bomber in Austria which wanted his message to be crackable, and he sent a message. Well, he was some right-wing asshole that was letter bombing people, and then he sent an encrypted message to the police, and the police tried to factor it and try to decipher it, hoping it would be the list of the next victims. In the end, it was not, but this person was actually using very close to a power of 2 in order to have people crack it. In the end, it was just some propaganda, some right-wing stuff as well. But so there are people using this for breakability. I'm not aware of people actually using this as an accident. But what can happen to you is not using close to a power of 2, but saying, well, okay, I learned I shouldn't be close to a power of 2, so I take some offset and take the next prime. Next prime just means add 1, check is it prime, add next one, add 2, add 3. Just check primes linear from then on. Now that we've done all this work, we finally found our prime P. It's a good prime. It is not anywhere close to a power of 2 because my C was large enough. Made it. Good. Now I want Q. So again, call the next prime. So I do P, P plus 1, P plus 2, till I find a prime. That means that if you take the product of the two, then this n is very close to a square. So this n is cooked up with this method. You don't see anything on the end. There's nothing wrong there. But when you compute the square root of it, it is almost an integer. It's .9999999, and then, okay, some dirt here. So then you know that your primes were too small. I mean, sorry, not too small, too close to each other. So if you ever take an RSA factor modulus and you compute the square root and you see something like this, then you know that user did this method. And then, well, you could just say, oh, well, I take the number, subtract 1, subtract 2, just going from the square root. Or you can check how far away is it, or how far away is it from being a square. So you take the seeding, that means the closest integer counting upwards. So just rounding this to here 57 instead of 56. Compute the square of that and subtract n. Now in this example, that is 4096, which itself is a square. So the difference of n and a square is a square. And then I take the 64, take a minus 64 and divide n. It's an exact division, so I found one of the factors. And then there's the other factor. So it doesn't matter whether it's a power of 2 or a power of 10. What matters is that the numbers are too close. Now this method actually works surprisingly well even if you don't do next prime. So here's another example where I didn't do the next prime, but did something larger. So this is not really close to a square. There's some 9s, but not too many. What we did before, we wrote it as a difference of squares and then divided n by one of these two factors. Now, in this case here, I would not start just a square minus n, but I say, well, if a square minus n is not a square, I try the next one. I do a plus 1 square, a plus 2 square. Each time subtract n and check when is this a square. Now for this example, I get lucky after 2. And this actually took me a long time to cook up this example because I was starting with something which was half of the bits of p were changed. So I was actually starting with a q quite a distance away. And still, most of those were just giving a square. We're not giving me anything larger than 0 here. Now, for general numbers, if I wouldn't do like next number, but just, well, random prime, another random prime, it still works, but it takes a long time. Because, well, I can always write it this way. This is A, this is B. But then usually it would take about square root of n, which is the same size as p, till I get there. So this is a nice method if it looks like lots of 99999, and otherwise do something better, as Dan will tell now.
Okay. All right, so it's bad to have P and Q too close to each other, or have small p, or to have P and Q non-random. So let's do everything right. Let's make just independently, choose some big P between 2 to the 511 and 2 to the 512, and choose some big q without being like the next prime or anywhere in the ballpark of p. You could maybe even say q has to be between 2 to the 509 and 2 to the 510, and then it's definitely nowhere near p. And now you get this public key, and p times q, which is a 1024-bit RSA key. If nothing's gone wrong with your randomness generation, then what does the attacker do? Well, we don't know anything fast. So this is going to be the one part of the talk where there's these big powers of 2 for how fast things are, because they're not really fast. And you have to think about how much something like 2 to the 80 is. There's all these different methods. I'll just skip down to the last two. There's a quadratic sieve, QS, and the number field sieve, NFS. These have been around since, well, the quadratic sieve since the 80s, the number field sieve since the early 90s. And the number field sieve, the general consensus is it takes something like 2 to the 80 operations. Now here's something fun to try. If somebody says 2 to the 80 operations and there's some cryptographer talking about the security of something, ask them, what do you mean by an operation? How fast is this operation? And then most of the people saying this will go running, screaming, like, I don't know what an operation is. Don't ask me that question. But still, people will confidently tell you that the number field sieve takes 2 to the 80 operations to break any 1024-bit RSA key, even if the user hasn't done anything wrong, the implementer hasn't done anything wrong. And this number, this 2 to the 80, if you pin down what those operations are, this is something which is doable today by people with a big botnet or people with a big computer cluster. Now, I'll give some details of what I mean by the sizes there. As your computers get cheaper and cheaper, somehow chips aren't going up in clock speed, but they're still getting cheaper. You know, you can get a really cheap ARM which is doing the same kind of computations that a pretty big CPU was doing several years ago. And chips are going to continue getting cheaper for a while. These attacks against RSA 1024 are going to become doable for more and more people. So how do these methods work? I'll give one example and then one little Sage script. And let's try just a really small number. This will be with a quadratic sieve, which is not as fancy as the number field sieve, but it'll give you some idea of how these methods work. The quadratic sieve starts with that Fermat method you heard about. Remember, the idea there was to try to find a square as a squared minus n. So a was like the square root of n, or maybe that plus 1, plus 2, and so on. And you keep searching for a plus 1, and so on. Search for numbers that if you square them and subtract n, then you get a square. So let's try that for n equals 2759, which is not very big. Then you try 53 was the ceiling of the square root. Square that, subtract 2759, you get 50. Well, 25 would be a square, but 50 is not a square. It's 2 times 25, 2 times 5 squared. And then you try another number, 54 squared minus 2759. 157, that's too complicated. I don't remember that being a square, so let's just skip it. And then you keep going like this, 266, 377, 490. I remember 49 as a square, but that doesn't mean that 490 is a square, because 10, 2 times 5, that's not a square. And 605, you can try, okay, wait a minute. We remember how to take out the 5, and then 605 divided by 5, well, you can figure out it's 5 times 11 squared. Oh, it's almost a square. So you keep doing this for a while, and it seems like Fermat's method is actually working pretty badly. It does work eventually, but it's taking quite a while. Here's what the quadratic sieve does. From the same computation, you look at these numbers that were not exactly squares, 50 and 490 and 605, and you notice if you multiply them together, 50 was 2 times 5 squared, 49 is 2 times 5 times 7 squared, 605 is 5 times 11 squared, and then you multiply those together, you get 2 squared and 5 to the 4th and 7 squared and 11 squared, and that's exactly the square of something. The square of 2 to the 1st times 5 squared times 7 times 11. And then the quadratic sieve is taking the square root of that number and subtracting that from the product of the 50-somethings that were on the left side and taking the greatest common divisor of that with n, and amazingly, that produces a factor of n. And it's not just, oh, some random accident that if you had tried the greatest common divisor of write down some hocus pocus, then yeah, you'll eventually get 31 coming out. Every 31 times you write down a random number, it'll have this 31 dividing it. Now, you can try this for bigger and bigger numbers, and actually this keeps working. As soon as you find a square product, then half of those square products are going to factor n. So that's how the quadratic sieve works. And here's a more systematic script for it with a much bigger number, which if it were just hocus pocus, this wouldn't work. But this does work. So there's a number from my computer's random number generator, 3141592653589793323. You try writing down a bunch of squares. Maybe I should get my computer's random number generator checked. It is that 2-year-old laptop you heard about before, so I'm not sure it's working properly. You take a bunch of a squared minus n, and then let's make a list of those, call it x. And you can see the range there is up to 500,000 numbers. So it's a pretty big list we're talking about. And then search through those elements, search through those a squared minus n, those differences, the elements in this list, to see which ones have easy factorizations. Now, a lot of them are numbers like that 157. I don't know what the factorization of that is. But there's a function which you can find on our website, easy factorizations, which looks through the list x. And if it finds numbers that are easy to factor, then it quickly writes down the factorizations using the small prime techniques you heard about. And then makes a list of the easy factorizations, put those into F. And then there's a big chunk, which I won't try to explain, which is called linear algebra mod 2. And that somehow figures out a square that comes from the factorizations. Like somehow it looks through this list of factorizations and magically applies some linear algebra stuff in it. Well, okay, I won't go through that. It's something doable. And this is using some standard Sage functions to do it pretty easily. Okay. There's all sorts of things that, in the interest of time, I won't get into, like how this easy factorizations works. And this is something where people write papers and papers and papers talking about trying to make this go as quickly as possible. I do want to emphasize one fact about these methods, the boldface, very small memory requirements. You can use the elliptic curve method that you heard about before. You can use that to figure out easy factorizations using very little memory, which means you can build a chip like an FPGA special purpose ASIC. You can have thousands of little ECM units running in parallel. So you can really massively parallelize this easy factorizations function. So if people tell you, oh, you need tons of memory for sieving to find easy factorizations, then you should tell them, no, no, that's not true. ECM you can do with very little memory and run it massively parallelizable. And then there's other things which, I suppose if we had another hour, then we could get into all these details of like how the number field sieve goes beyond this. It's a similar kind of method, but gets more complicated. I do want to emphasize, again, one thing in boldface here, which is that if somebody tells you, oh, 2 to the 80 operations, the attacker wouldn't do that because the target isn't worth that much to them. Well, batch NFS is a way to take a bunch of n's, and like the batch techniques before, there's some magic ways to find redundancies between doing the factorizations of those n's. So if somebody tells you, oh, 2 to the 80, that isn't worth it for the attacker, well, batch NFS reduces the cost quite a bit for factoring each key. If the attacker has a lot of keys to target, they can factor all of them in not much more cost than just factoring one. So don't believe people who take an economic view of how much the number field sieve is worth. All right, what does this mean? Can the attacker actually do the number field sieve once they've put in all these optimizations? Well, if you look carefully at the analyses of the number field sieve, only about 2 to the 70 differences, things like these a squared minus n's. If you look through 2 to the 70 of those and scan them properly, find easy factorizations, do linear algebra, you will factor into any 1024-bit key. Now 2 to the 70, how big is that number? Well, it's actually small enough that you can do this computation on your favorite botnet. Say, okay, Conficker is shrinking still, and it'll probably be wiped out at some point, but it's an example of what you can do using any of the security problems that are deployed on enough machines. You can break into a bunch of machines, millions of machines. Conficker estimates vary between 7 million and 12 million machines. So you use your, say, 2 to the 23, that's 8 million machines, count how many seconds there are in a year, and then say, okay, that means we have to do 2 to the 22 differences per second per machine, and that is slower than state-of-the-art factorization code already runs. So it's actually a pretty easy computation. You don't even need that many millions of computers to do this. If people tell you, wait a minute, you can't just use a bunch of machines, there's all this work for linear algebra, then I'll just skip this. Be aware that linear algebra is not as much of a problem as some people would say. If you use a big botnet, there's one little problem. For an attacker who breaks into a bunch of machines and then starts spinning them up, heating up the CPU, the fan starts running, the user starts wondering, why is my machine running so slowly? Maybe only use half the CPU, but it's still got a good chance of getting you detected and kicked off the machines. Users are going to shut you down if you're doing, say, a year of computation on your botnet. So what do you do instead? Well, you build a little computer cluster. Now, yesterday we've heard about a big building in Bluffdale, Utah that apparently is going to store all of the data collected by the NSA for the next 100 years, or maybe forever. But something that I didn't hear emphasized yesterday was that this building also has a new power substation, which is drawing 65 megawatts, well, generating 65 megawatts. Now, what are we doing with 2 to the 65 megawatts? Is that the kind of power that you need to store a bunch of data on tapes? No, that's the kind of power you need to do computations. So what is NSA doing with 2 to the 26 watts? Or maybe even with more watts? You shouldn't actually think that 2 to the 26 is such a big number. Here's a little table of, well, 2 to the 57 admittedly is pushing it a little bit. This is the total power that the Earth gets from the sun, of which about half gets to the Earth's surface. 2 to the 44 is the amount the human race is using right now. Varies a little bit, but I mean, this is the average power, including cars and such. If you have the botnet that breaks into millions of machines and runs them flat out, that's about 2 to the 30 watts. And actually, if you think about it, wait a minute, there's a lot of machines out there. This means that 2 to the 26 watts is not actually that much power. It's just one dinky little Bluffdale 65 megawatt computer center. And actually, if you're a government agency, you probably have more than one of those, as you heard yesterday in the context of data storage. But again, it's not just data storage. You don't make a 65 megawatt power station to just store data. Okay, if you just take standard graphics processing units and run 2 to the 26 watts of those, that will do about 2 to the 84 floating point multiplications per year. And then you have to figure out, okay, what exactly are the operations involved here? This should be enough to break 1024-bit RSA. And if NSA is not just buying GPUs off the shelf, but really tuning chips that they build, actually they're using IBM to manufacture their chips at the moment. Apparently it wasn't cost effective for NSA to manufacture their own chips, so in 2005 they started subcontracting for IBM, but presumably through that fabrication, IBM is building chips that NSA wants, and those should be about 10 times faster than what GPUs can do. So it should be possible with this little 65 megawatt computer cluster to factor at least 1, maybe even 10, and then with batch NFS, maybe even more RSA, 1024-bit RSA keys in a year.
So to conclude things up here, I want to explain how you can use, from the comfort of your very own home, a distributed, a massive scale distributed cloud computing service to calculate private keys on your own. So many of you may be familiar with Amazon EC2, but it turns out, Google also has a large amount of computing infrastructure, and they actually have a really convenient web interface to access it. It's amazing what you can find on the internet. So, okay, here are some keys. Except, if you look at these carefully, not all of these are sort of obviously RSA keys. There's some problems here, like the second to last one on the bottom. So, after doing this search, we found this key, and yeah, someone seems to have pasted a private key into pastebin, and someone came along and interrupted part of it with some profanity. But this is an interesting problem. What do we do with this key? I mean, clearly this is an interesting key. We must have this key. So. Well, we'll discuss this.
Questions will be later after the talk, please.
Okay. So, yeah, okay. We have removed the obvious problems here. But there's still an issue, which is that we are missing hundreds and hundreds of bits of key. I mean, we can't brute force this. What are we going to do? Well, okay, let's look at what RSA keys actually are. I mean, I introduced RSA keys, and I was like, okay, it's a D, and D has like thousands of bits. And, you know, if we don't know P and Q, how are we going to get this D? Well, so here is the storage format for an RSA key. So, you know, public key is, you know, the modulus n, the public exponent e. Okay, private key has version n, e, d, the decryption exponent p, q, d, d mod p minus 1, d mod q minus 1, the inverse of q mod p. This is, you know, all useful information if you want to speed up your calculation and not have to compute everything every time you use your key. Okay, what did we see here then? Well, here is the key broken up into all of the different pieces. So we have, you know, the red bit is approximately where n is sitting. We've got e in orange. We've got part of d in yellow. We seem to be missing p, but we've got part of q. And then here's d mod p minus 1 and d mod q minus 1 and q inverse mod p. There's also a little problem before the red here. In addition, you might call this the private part of the private key. Fortunately, this is just sitting in an encoding of like the length and the version. So. All right, so what do we do with this information? Well, you know, basically given any part of this private key, we can easily compute all of the other parts. And, you know, simple formulas, Q, well, we take, you know, the, 2 to the, like, E times D mod P minus 1 minus 1, and GCD that with N, and, you know, then we get Q, and then we can figure out what P was by dividing, and figure out what D is, and so on and so forth. And, you know, you can do this even if you have a part of a single value from the private key. You can still compute the rest of the private key from that. We don't have time to get into this, but it's online. So, you know, using a little bit of math, single formulas typed into Sage, we can reconstruct the private key here. So what are the lessons that we can learn from everything that we've done today? Well, the first one is stop using 1024-bit RSA if you haven't already. And I have looked at the keys that are out there on the internet, and you are still using 1024-bit RSA. Second, of course, make sure your primes are big enough. Don't try to be clever about how you're generating them. And make sure your primes are random. You guys have some problems, especially in hardware. Also, fuck a duck is not good crypto. Pastebin is not secure cloud store. And you probably shouldn't put your private key in a secure cloud store anyway. And lastly, thank you.
Give a round of applause. So questions will be taken at the numbered microphones. So anyone who has a question, please line up at a microphone, and we will start by the Signal Angel, who has a question from IRC.
So IRC has a lot of punchlines involving penises and some questions. So the first question is, so would you recommend more using elliptic curves or RSA with multiple primes using proper primes?
So there are ways to do elliptic curves wrong. There are ways to do RSA wrong. In general, if you've got a particular performance requirement, then elliptic curves are going to meet that with a much higher security level than RSA is going to meet that. Of course, you can do RSA securely, you can do elliptic curves securely, but if you've got some performance limitation, as many applications do, then elliptic curves tend to be a better choice.
I also want to clarify, so the other most commonly used public key crypto system is DSA, the digital signature algorithm. There's also elliptic curve DSA, which is probably what you're thinking about with elliptic curve cryptography. And DSA is, in my opinion, actually much worse than RSA in terms of randomness failures. In the paper that Dan referenced, we also talk about randomness failures in DSA, and it's horrifying. If you ever screw up randomness in a single signature, your entire public key is lost.
We will take the next question from microphone number 4 to the right of the scene.
Hey guys, sorry I didn't mention the computing power at Bluffdale. That said, when we want to transition from 1024-bit RSA to something else, what do you think is a good idea? So for example, in Tor, we do use 1024-bit RSA for TLS. And yeah, I know, right? So the thing is that we're working on changing these things, but Zuko has this 100-year crypto project. But, what is the real thing that we should, like if we could switch tomorrow to something, what's a useful thing that we can live with for 5 or 10 years? Is 2048 going to be useful? Is 4096 where we should go tomorrow? Because there is a trade-off between performance and forward secrecy, and there are a lot of things to think about.
Okay, if you tell me 5 to 10 years, I would be still comfortable with elliptic curves. If you talk 100 years, and then there's all these worrisome quantum computers around, then I would go for something which is worse in performance, like code-based cryptography or for signatures hashing. But if you're saying 5 to 10 years, I'm very comfortable recommending to you elliptic curves with 256 bits.
Okay, thanks.
Signal Angel.
Yeah, another question from IRC. So if you avoid all the easy primes, doesn't that shrink the search space such that it becomes easier to crack the remaining keys? Or asked another way, can you quantify the ratio of easy prime versus hard primes?
Yeah, it's a good question. So the answer is yes, it can be quantified, and once you're up to about, say, the 1024-bit RSA key level, then there's very, very few weak primes. So if you have a random number, you just generate a random prime, then your chance of bumping into something weak is so small that you just don't have to worry about it. It's one of those much less frequent than being hit by lightning kind of events. So it is something which has been quantified, and it is an issue for smaller RSA keys. Back when people were using, say, 512-bit RSA, then it was actually a noticeable issue. But once you're at 1024 or above, then the issue is basically gone. It's something where you can and you should look at exactly what the chance is of bumping into a weak key, but it's not realistically something you're going to encounter with 1024-bit RSA.
Okay, we're going to take the next question from number 1. Just one notice, we don't have a lot of time left, so even though there is a talk
an important
before
question.
1 hour, just ask.
There is a devastating attack that can break AES, SHA-2, most probably SHA-3 and DES. It's called the big click attack. Are you concerned that it might break RSA with any key size and even ECC and even any public key crypto?
No. So byteclicks are something which are certainly interesting. I think about it as a way to speed up brute force, and it speeds up brute force by a noticeable factor, often makes attacks, say, twice as fast. But with public key crypto, we have attacks which are much, much faster than brute force to begin with, so that kind of speed up of brute force won't be competitive with things like the number field sieve.
Next is from number 3.
Me not coming from the dark side of mathematics, how do I know that my random number generators are fine for generating keys?
Seed them. Basically, the things that are out there, if you're using a standard random number generator like in Linux, actually Linux has added patches to the kernel to fix some of the problems that we found. If you want to know that your keys are good, if you generate them on a general purpose computer after it has been running for a long time, you are probably fine. I would not generate very important or long-term keys on lower power hardware devices where you can't tell.
Thank you.
Next question will be taken from number 4.
Hi, it's just a remark, not really a question. I work in high performance computing. I was at the supercomputing conference a couple of weeks ago. They are presenting large scale installations and dealing with problems of power. They want to build petaflop and exaflop systems that are in the range of 20 megawatts. So I'm wondering what NSA is doing with 53 megawatts in a data center, because I know storage doesn't take that much capacity. So I think it's really something we should think about. So thanks, nice talk.
Next question from the Signal Angel level.
Okay, another question is, how big do you estimate the effort to exchange keys and certificate involving 1024 bits primes, let's say worldwide at the moment?
I guess I wasn't getting what the question was. Could you repeat the question?
I don't really understand it myself.
Okay, just let's switch to 1.
Yeah, my question goes back to the idea: how can we know how good the keys are, private keys are? Is there something like a keygen evaluation tool, or can the quality of a key generator be estimated from a sample of keys, like a public tool that I can throw keys on and it will tell me a bias of my keygen?
If you go to factorable.net, my co-authors and I have made a key check tool, which will tell you if your key is in the list of keys that we scraped off the internet that we were able to compromise. That's a first check. It's not a positive verification that your key is good, but it will tell you if it is very bad. If you want to check your
Key generator. Actually.
If you want to check your generator, if you're worried about the factorization problems, we have fast code on the website in C that will do the GCD calculation for you if you just dump a gigantic collection of keys at it. If you might have other problems, like you are not sure whether it's factorable, like those don't come up, the experiment that you might want to do is sort of restart the process in realistic conditions and generate a gigantic quantity of keys and just check for repeats. I mean, the sort of obvious stress test things, I mean, if you have a device, you want to boot it up in realistic conditions and then check them. And this is painstaking work, but I don't think there's any realistic way of doing better than that. Or inspect the code, the obvious thing. Make sure you're seeding anything.
Okay,
you know.
Thank you.
So next question will be from mic number 4.
Hi. Well, if I got your numbers correct, so you said something like it would take 8 million machines a year to factor 1024. So I was wondering, what if I would like to factor like 800 bits or 900 bits, which is, as I understand, way easier than 1024, but was never done publicly. So are you saying that would take like a day or something?
So it depends on the size of cluster you have. The RSA 768 factorization a couple years ago used something on the scale of 1,500 computers for a year. And those were normal kinds of computers, desktop kind of computers with, I think, typically 2 cores. So nowadays, if you have some faster, say 3 gigahertz 4-core machines, I think those were typically 2 gigahertz 2-core. Yeah, nowadays, right. So Tanya's mentioning you, of course, want to use GPUs to speed things up. And there's many ways to take advantage of computer technology moving forward. To get careful estimates for going from 768 to 800, that's a short enough extrapolation that people are pretty confident about that. Getting to 900 starts getting iffy what exactly the cost would be. And 1024, there's a fair amount of guesswork. So there's some consensus on roughly what the costs are, but it's hard to say exactly. But again, to give you a scale of it, you were saying like 900 or 800. Well, 768, RSA 768 challenge was done, and that one was 1,500 machine years.
Okay, thank you.
We'll take 4 more questions from Signal Angel first.
Okay, so it's a clarification of the question I asked before. So, the actual question is, so how big will be the effort to upgrade existing keys from 124 bits to a 4K or 8K bits? So yeah, considering the keys that are currently in use, how much effort worldwide would it be to upgrade all that to something more secure?
Well, I mean, for the private user, if you're running SSH on your laptop, you can just generate a new key. It doesn't take you much time. You will notice maybe some degradation in performance if you're running it on a netbook, but going to 2048 is not a big deal. However, there's a recommendation from the US government to stop using 1024-bit RSA as of 2010, and we still see it everywhere. So apparently it is bigger effort than just everybody spending 10 minutes on the laptop.
Maybe part of the problem is things like, okay, everybody says, yeah, use 2048 or bigger, and there's some financial standard which says you can use any key size you want up to 1,984 bits. I have no idea how they came up with this, but then they run into some other standard which says use 2048, and they just can't implement it on the smart cards, which only support up to 1,984. Now, if you get the standards people talking to each other for several years, then they can agree on using 1,984. It's just about as good as 2048, but realistically, when you have these conflicts in standards, then it takes a while to work out. And when you have a busy server that's trying to do 2048-bit RSA, it doesn't matter what the standards say. If you've got a ton of load, you just can't handle that load if you're spending a ton of time on the cryptography. And that, again, is where we like elliptic curves, because they give you, for whatever your performance constraints are, much better security. So if you're trying to reach a given security level, the speed is much better.
Next question will be from number 2.
So you've had 2 developers stand up and ask how to verify whether or not their key generation is correct and whether or not their random numbers are correct. And I think it's great that you give coding recommendations like seed rand, but coming from a development perspective, I like to unit test my code, and specifically I like to write my unit tests before I write my code. It's called test-driven development. So if I'm going about creating an algorithm to encrypt something or whatever, what are the steps that I need to do when I'm writing my unit test to, so has there been some kind of effort in that way, like what goes into a unit test for determining that your random number is correct? I mean, there's algorithms for determining whether your random number generator is operating correctly, right?
Yeah, so this is something where there's, if you look at how the random number generators work, there was just a NIST workshop, and there's some NIST standards which are telling you, here's what to do to test your random number generators. So you have a hardware random number generator, some post-processing, and they say, okay, here's the standards for how to test those pieces. Now, that's not the same as testing the cryptography that's using those pieces, and it's very helpful if there's a clear separation there. So you have your cryptography, which is doing deterministic stuff, and says you have to have some randomness coming in from a totally separate unit, where the only job of that separate unit is do the randomness properly. And then the NIST tests will tell you what the randomness does, and then deterministic cryptographic testing will tell you that the other pieces are working correctly for all sorts of inputs. Where it goes wrong is something like the ECDSA standard that Nadia was mentioning before, and that's one that says that you don't just deterministically generate a signature, you make some new randomness every time you generate a signature, and that's what goes horribly wrong. So that's something where we need new standards which say, instead of doing what ECDSA does, we have a clear separation between the cryptography always does the same thing, making it testable, and then randomness is centralized in one spot, which hopefully the NIST standards do a good enough job of testing.
So there's something that says, here's what determines, like, I guess what I'm asking is, do you know of any algorithms that can be used for determining whether something is a good random number and whether your random number generator is generating things properly?
Well, there are a bunch of tests for, there's hardware random number generators where you can run them through the die-hard tests. There is certificates by FIPS. In general, I would recommend implementing all those steps, but the smart cards that were mentioned by Dan earlier from the Taiwan citizen card, those are actually FIPS certified. So even though these go through what is the industry standard of doing random number generation on smart cards, which everybody thought was good enough, apparently they're not. So randomness is a total mess. After the paper by Nadia and also the paper by the Lausanne team came out, there is now some more movement in finding better random number generators. At this moment, well, hope for the best. Implement the standards, yes, and if you have some source of randomness, try to stretch it with a stream cipher or something like that.
I want to tell a little story. After we published the paper, I heard some very interesting things from some of the vendors, and I think one of the things that makes randomness and cryptography a difficult problem is that this kind of issue is something that crosses a lot of the abstraction boundaries that you're used to in coding. You want to have the clean unit test that you know that this piece works and this piece works and this piece works and this piece works, and you put them all together and it will all work flawlessly. And somehow this kind of problem is something that happens at the boundaries of each unit test. We know that the operating system is like, okay, I'm getting my proper inputs from the hardware, and I correctly generate my randomness from there, and then the application says, I'm getting my randomness from the operating system, it's good randomness, and then the application uses the correct crypto algorithms to then do cryptography. And at the very beginning of that stage, there was something broken, and it translated all the way through all of these pieces of software that were working correctly. And testing this holistically was the only way to find this kind of error. So one story that I heard from a vendor was that they ran into randomness problems. They had developed some device, it was working perfectly, and on the assembly line, they were being turned on and run through the checks on the first, you boot it up and it checks the integrity or something on the assembly line, and it was continuing on. And if you exactly booted them up in the exact, at the exact same time, in the exact same conditions, then all of the inputs to the random number generator would be the same, and they would generate the same keys. And then those keys would be, they already generated their keys, so they wouldn't generate them again after they went, to the consumer. And I don't know how to unit test that except take the entire device and turn it on and take multiple of them and make sure that the devices, as they are coming out of the production process, are working correctly.
So we will take two more questions, one from number 4 first and then number 1 at the last.
How good do you think hardware-supported random numbers generators are? After what you just said, I think they are probably not good anymore. You don't know.
Well, Intel has their RD-RAND instruction in some of the newer chips, and they say that they've gone through a reasonable number of evaluation steps. It sounds like they're trying. Whether they're successful is a different question. Something I don't like about the API is that RD-RAND gives you no way to test the pieces. You can only test the post-processed output, so nobody else is able to test the actual randomness generation part of the hardware. You can only get a filtered version of that. So Intel and people who are contracted by Intel to see what's going on inside are the only people who can run these tests. It's not open in a way that allows the community to see if there's further problems. But at least they're trying. And maybe with enough effort, the hardware manufacturers will get randomness generation right. Of course, if you can generate any sort of secret once, if you have enough of a secret to start with, then you can use things like AES to generate any number of secrets, and you can put those secrets into any number of devices that you want. And if you use AES in counter mode with encrypting 1, encrypting 2, encrypting 3, you'll get totally unpredictable, unrelated outputs, and then burn those into some hardware. But where do you get that initial randomness from? Are you going through a trustworthy process there? It's a hard problem.
Next question from number 1, and that's the last question.
You said something about, you dropped this group-based cryptography word. Most of the stuff I've encountered under that heading kind of sounded like snake oil, just because they were using non-abelian groups and stuff. Is there anything you hear that isn't?
Okay, I did not say group-based crypto, I said code-based cryptography.
Sorry.
So there is a
Thanks.
class of crypto systems which are fine against quantum computers. For all crypto, it's always up to what we know. I mean, next day there could be somebody with a polynomial time factoring algorithm and so on. Now there's also a group of people doing braid group cryptography, doing non-abelian groups. Most of these systems have been broken. If they weren't broken by classical computers, maybe they would remain secure against quantum computers. It's lots of woods there, I mean. So yes, they might have this on their flags as well, but I wouldn't count this as a secure system. Whereas code-based cryptography or lattice-based cryptography are systems which should be fine.
Maybe just a URL, if you're interested in post-quantum cryptography, is pqcrypto.org, and that keeps track of papers on the various types of cryptography that should survive for 100 years, and well, in particular against quantum computers.
Ladies and gentlemen, please give Nadia, Tanya, and Daniel a big round of applause. Thank you so much.